In today's video, we're going to take a look at redox reactions, which are reactions in which oxidation and reduction both take place at the same time. And to do this, we'll cover displacement reactions, ionic equations, and half equations. We saw in a previous video that one meaning of oxidation is the gaining of oxygen, and that reduction is the loss of oxygen. For example, if aluminium reacts with oxygen to form aluminium oxide, we can say it's been oxidized. Whereas if we take away that oxygen, then it's been reduced. The terms oxidation and reduction can also refer to the loss and gain of electrons though. And instead of just remembering which is which, most people use the mnemonic oil rig, which stands for oxidation is loss, reduction is gain, and this refers to electrons. So if we had a magnesium atom, and it loses 2 electrons to become a 2+ ion, then it's been oxidized. And if it gained those 2 electrons back, then it would have been reduced. Most of the time though, these oxidation and reduction reactions don't happen by themselves. Instead, they both take place at the same time. Because if one substance loses electrons, then another substance has to gain them. And because both happen together, we call them redox reactions, which just means reduction-oxidation reactions. For example, if we react some magnesium with a dilute acid, which we can represent as H+, because that's the important part of an acid, then the magnesium atoms will lose 2 electrons and be oxidized, forming magnesium 2+ ions. Meanwhile, the hydrogen ions will gain those electrons and so be reduced to neutral hydrogen atoms in the form of hydrogen gas. Another place we see redox reactions is in displacement reactions, which involve a more reactive metal displacing a less reactive one. For example, if we look at our reactivity series, we can see that calcium is more reactive than iron. So if we added some calcium to a solution of iron sulfate, then the calcium would displace the iron to form calcium sulfate, while the iron would precipitate out as a solid. For reactions like this, it's sometimes useful to write them as ionic equations, in which we only show the particles that actually take place in the reaction and change in some way. For example, if we showed everything here as ions, we can see that the sulfate ions stay as SO4 2- ions. They don't actually change or take place in the reaction by exchanging electrons. Because of this, we call them spectator ions and get rid of them from our equation. And what we have left is the ionic equation. We can actually break this down even further though, by writing individual half equations which show the gain and loss of electrons for each of the elements involved. To do this, we first copy the ionic equation, but only for one particular element. So for calcium, we would write that a neutral calcium atom goes to form a calcium 2+ ion. Next, we need to add our electrons to make the charges balance. As the calcium atom loses 2 electrons, we can think of the calcium ion as one product, and the 2 electrons as another product. So we put +2 electrons on the right-hand side. Then for iron, we show the iron 2+ ion going to form an iron atom, and then again think about our electrons. This time the iron ion gains 2 electrons, so we place the 2 electrons on the left, because they have to combine with the iron ion. Whenever you do these half equations, just check that the overall charge on each side balances. For example, in our iron half equation, we can see that on the left we have a 2+ charge and 2 1- charges, which add together to make 0. And on the right, everything is neutral, so also 0. If you ever find that the overall charges on each side aren't the same, then you've probably put your electrons on the wrong side. Anyway, that's all for this video, so if you enjoyed it, then please do tell your friends about us, and we'll see you next time.